If you guys were in the classroom this year, we'd be running this experiment. It's a very boring experiment in which we take ice and we see what temperature it is, and then we just heat it up until it all boils away. And we take a look at what the temperature is over a period of time. So if you take a look at this graph, our temperature is our y-axis, our energy is our x-axis. We could also think of that as time because we're heating it up over a fire. So the more time goes by, the more energy it will be absorbing. And that ice starts out below 0 degrees Celsius. And once it starts melting, I want you to know, see there, as it starts melting from point B to C, there is no temperature change. So as that ice is melting, it is 0 degrees, and it will stay 0 degrees until all that ice melts. Once all the ice melts and it's all water, then the temperature will start increasing. So we can't have the phase change and temperature increasing at the same time. Once you hit that melting point, that is when it starts to melt. Once we hit 100 degrees, and this goes with what I said earlier, once we hit 100 degrees, it starts boiling. It doesn't get any hotter than that. All the energy added to it goes to turn the water into water vapor. It goes to boiling it. It doesn't go to increasing the temperature anymore. So up to now, we've been able to use this formula. Heat equals specific heat times mass times change in temperature. But during a phase change, something could be absorbing heat, but not changing temperature at all. So we're going to have to be using a new equation. And this special heat, I know it's covered right here, but this heat that is used to change the phase and doesn't increase in temperature, that is called latent heat. And that's the word that's blocked right there at the bottom of the screen. Sorry about that. So we just talked about endothermic and exothermic. Something that is endothermic absorbs heat. So when we melt something or when we boil something, that is endothermic. When it goes from a gas to a liquid, when it condenses, or a liquid to a solid, when it freezes, that will be considered exothermic. So as we sweat, we are releasing, we're sweating, and the water, the sweat, I should say, the sweat on our skin is evaporating, and that is absorbing heat from our body. So our bodies are exothermic when we're sweating, and our sweat is endothermic. It's absorbing that heat and evaporating off our body. All right, so I don't have a lot of time, so make sure all this gets in your notes. Enthalpy of fusion is the amount of energy it takes to melt or freeze a substance. And I want you to note, melting is going to be taking energy, so it'll be a positive number. Freezing something is releasing energy, so it'll be a negative number, but they will be the same number. Just melting will be positive, freezing will be negative. Enthalpy of vaporization is very similar to the enthalpy of fusion, except it's the amount of energy to vaporize or condense a substance. And here, boiling would be endothermic, so it would be taking energy. Condensing is exothermic, so it'll be negative. And I think I may have said that backwards up top too. So melting is endothermic. It is absorbing energy, so it's positive. Freezing is exothermic. It is releasing energy, so it is negative. So now we have to use a different equation for when we are calculating heat, when something is freezing or melting or boiling or condensing, and it'll be right here. So it'll be heat is equal to the amount of our enthalpy of fusion if it's freezing or melting, and heat it equals the amount times our enthalpy of vaporization if it's condensing or vaporizing. Make sure your units cancel out because sometimes they give you different units. So make sure to write those equations down. And then here are a couple examples.